We're going to talk a bit about dipoles or dipole moments with regard to magnetics and magnetic fields. And a dipole, and a dipole moment is essentially the equivalent, magnetic equivalent to charge in electrostatics. So if something's got a charge build up, you can have a dipole moment build up. And sort of what is it? You can measure charge by rubbing two surfaces together, getting a charge on one, and seeing the force between it. And a dipole moment is very much in the idea of the torque force. So torque force in a uniform magnetic field. So whereas a charge is a charge in a field, a dipole moment is the torque force in a magnetic field, and it's got a sort of a unit. So if you can imagine, I've got that's the south pole, and this is the north pole facing towards it, and it takes energy to move it away. So much energy to move it away. You can measure the strength of a dipole moment in units of joules, the amount of energy, by the actual size of the field. So it's joules per Tesla for it there. I'm stewing away these mosquitoes. I'm enduring as I'm giving this lesson to you. Now the actual word dipole is perhaps a little bit misleading, because you can get an electric dipole, a positive and a negative charge, and the field lines will go around, and then you can take that away, and then you can replace it without the bunching to the actual poles. It looks almost like a magnetic dipole, but in fact there is no two individual poles. There's actually no pole in a dipole, so that's a little bit confusing, and it comes from an ancient or an idea which sort of occurred and sort of disappeared and has appeared in schooling, but not is that you can make a magnet out of a north monopole and a south monopole, or it can be defined by an Ampere's magnet, which is a loop of current. And I want to get down to the dipole moment. So something called a dipole moment is equivalent to a charge. So an electron has a charge of 1e, a tiny fraction of a coulomb, and a coulomb per second is an amp, just to remind you of that. And so I can say 1 amp or 1 E is something like 9 to the minus 1.6 by 10 to the minus 19. I really can't remember it, of a coulomb. It's the same thing. You can put an E or 1 amp, E in any of these formulas to go around. Well, it's slightly different to go around these formulas. So the magnetic field, by definition of what B is the loop current around a point from Maxwell's equation. So like a really doggy sort of like a mechanical electric circuit, which does one of Maxwell's equations, which is curl B equals J. I think there's some units in there, but there's a mu in there. Yeah, there must be. Except it really gives you the solenoid formula, which is the B in a solenoid is proportional to the current loop, which is the number of wires per unit length times the current in it, times mu naught, which gives you the conversion factor down to Tesla, from amps to Tesla. That's gives you the magnetic field generated by this current, and it's different from so the electromagnetic moment is not the strength of the electron magnet. It's the actual the magnetic moment is the energy per 1 Tesla to rotate an electron around. Now it turns out that you can't actually rotate an electron around. It's SU2 symmetry. It's not our SU3 symmetry, which is our, like a twig or a piece of leaf is SU3. I'm SU3. it's SU2 symmetry. So an electron, you can't actually rotate it. It's got no size, no shape. It's got no parts to it, so you can't grab the top part of the electron. It's allowed because it's a fundamental particle, and in fact it's equivalent to actually pulling it through. Well, not in the dimensions that we understand. This is when spin flips, it actually doesn't flip, it pulls through. But regardless, so what happens is that it has demonstrable properties, but it has no mechanism behind it. It is a fundamental particle. So fundamental is really our way of saying, for all intents and purposes, for an SU3 person like myself and you, it appears like magic. And then we can show you how it does it by giving you some maths, which is it's conceptualizable. It's not imaginable. It's you can comprehend it, but you can't imagine it. That's the best I can say. So we've got our electron, and we have the solenoid story. We have another story, which is the motor story. That is the torque on a loop is I times the area. So if I have an amp going around a square meter in a 1 Tesla thing, it will have a 1. What is it? What would be one? I wonder what the torque formula is. It's got a torque of 1, whatever those torque units are, and so it's the moment is B times the moment is the torque, and the moment is the I times the area. So it's the I times the area. So the I, you've got your loop, and you've got the area of it. Now for an electron ostensibly orbiting an atom, okay, so we've got an atom, and we know it doesn't actually orbit, because if it orbited it would radiate. It does something, it does the quantum mechanical equivalent of orbiting, and that is its phase changes. So it's got orbital angular momentum with its complex phase. So it's complex. If you could watch its phase, the phase would clearly go around at the required frequency. Everything would be hunky-dory, but it physically has got no mass moving, because it doesn't have a part, but it does have mass in there. So it's got the fundamental properties of it, but not actually there. But we've got this electron. Say we've got this electron orbiting like this, and we want to find its moment. So it's charge times its area. So like the torque on a motor. You know, a motor is the I times the area times and the actual the moment across the field gives you the amount. So the field's like this. The torque is maximum there, and minimum when it's flat to it. Your cross to it. I was trying to work that out. It's B dot I. So it's B. Oh yeah, your area is pointing up. Your B is that way. It's the cross for it. But getting it in, it's I times A, and it's an electron going around a nucleus. So it will. So its velocity will be the current will be the number of times that electron passes a point per second. So it's E, the current, divided by the period, and the period of an electron, something going around there, is that if it's 2 pi r divided by v, so it's E times its velocity on 2 pi r, then times its area, and its area is pi r squared. Okay, so the r's cancel, the pi's cancel, and you've got E V R, E V R on let's see, EVR on its EVR on its on 2, EVR on 2, and MVR is the mass times the velocity is its momentum times r is its orbital angular momentum. So you get the moment, the classical moment of an electron, as equal to E on 2 times the angular momentum, which is L. That's all okay, except if it's SU3 space, which it is for an electron going around an atom. That's perfectly okay, and you can stop it radiating by actually saying, well, its speed is seen not by its physical movement, that is, its speed is not conceived as the Greek would see speed. So we would say, I can see this object here at this time, this object here at that time, it's time, distance. It doesn't go like this. The actual phase of this leaf is changing all the time. It's like an octopus striping through all the time. And if I do the formula for momentum on that leaf in complex numbers, that gives me a speed. So we've got the L for angular momentum being E on 2L, whereas for spin it's 2, the gyromagnetic ratio, E 2E divided by, sorry, you've got to divide it by the, I hope I said this, you've got to divide it by the mass of the electron. You've got to get the mass of the electron out to get out the angular momentum. So the lighter it is, the faster it must be spinning around. So the mass of the electron is down there, and then you have the gyromagnetic ratio, so that's 2E on 2 divided by the mass of the electron times its angular momentum, which by quantum mechanics is fixed to be h, Planck's constant, on 2. I haven't done too well on that one, but I'll try and say that one again and keep on working on it from time to time. Hope that's made sense. So that's what the dipole moment of an electron, orbital and spin.